Welcome everyone to this new episode of Among Us, human-robot teaming. It's a real pleasure to be here today because one of my historic students here at the University of Agder in Norway is here with me, Martin Økter. He's a PhD student now, a PhD candidate working on topics directly related to the to human-robot teaming. Martin, would you like to say something to our listeners?
Hi, Filippo, and thank you for inviting me to the podcast. I'm really looking forward to this.
Very nice to have you here. And as we always mention, this podcast is for everyone. It's not only for the big stars professors, but we also would like to promote the work of young, motivated PhD candidates that maybe one day will become professor star. Without further ado, I would like to introduce Martin Økter a little bit more formally. He's a PhD candidate at the University of Agder in Norway, and he is currently involved in one of the European projects titled Rhinoceros, where his research is focusing on something that is very much related to human-robot teaming. So if we think about the applications of the concept of human-robot teaming, we can, for example, imagine industrial applications and where you cannot fully automate the process. And specifically, the project that Martin is involved with is looking at how we can disassemble battery units from electrical vehicles. And in this specific case, there is a plethora, a big variety of battery units. And therefore, it's not easy to fully automate the process because every unit is slightly different. And even within the same manufacturer, you have different models. So therefore, Martin is exploring the possibility of using machine learning and specifically imitation learning algorithms where humans and machines can transfer knowledge between each other in a closed loop. So for example, at some point, the machines, the robots have seen several models of electrical or batteries, and therefore they can transfer that knowledge back to the humans. Or initially it could be vice versa. It could be the humans that have matured more knowledge and they are teaching the robots. So I think that this is very much in line with the concept of human-robot teaming, where there is a democratic balance between the two actors, machines and humans. They are not like it used to be, humans teaching robots, humans in charge. But today we are thinking about this shift of concept where humans and machines are more equal and they support each other. So for applications like recycling batteries, I think that the concept of HRT is very, very central. And Martin is going to tell a little bit more about this project. And we can start digging into a few aspects of this idea. So as always, we keep the same standard schedule. We have formulated 4 points of discussion, really not questions, but more open point of discussion. And the first point, Martin, is about the idea of using haptics. So what is haptics, first of all, and how you are considering to use it in your project and how perhaps you have used it in the past. We have been working together for several years now. You were one of my students, and I'm very happy to see the progress and to see the trend, the upward from bachelor to master to PhD candidate. So tell us a little bit more about the concept of haptics and how we can use this in HRT.
As you said, we did my master's together on haptics. Like for humans, I think it's so natural, you don't think of it, but we humans use so much more than a vision. Like, of course, we see a video and robots can see things with the video cameras, but we humans rely so much on our other senses. And one of them, which I think maybe don't think that much of, like, is so important, but touch and how we can actually interpret force is so important. So for a robot to like navigate the human world with just vision is unrealistic. So haptic is the thing where we actually interpolate this force sense also into the robot's computing and sensing. So we can also allow the robots to have like a more natural or human acting in the environment. And that's of course what we like, right? We want it to look human or do the human task. That's why we build humanoids, but we can't go there without haptics. So I think it's so exciting to work with.
Thank you, Martin. I think it's very exciting, as you said. And just to remind our listeners, the idea is to explore not just vision or auditory channels, but humans, as you said, have five senses. So we are convinced that one of the most important way to connect with machines, to connect humans and machines, is to explore the sense of touch. And that's what haptics means. Like we are closing the loop and expanding the interface between humans and machines by augmenting this perception also with touch. So we really believe that touch is so relevant. I mean, kids like newly born babies, the first sensorial experience that they start exploring is touch, actually. So, for example, if you give them a finger, they will grasp it. They use also other senses. For example, they use taste. Whatever they grab, they want to bring it to their mouth. So we also believe that the other senses will also start a new revolution, like taste and smell. They will probably be at some point part of this concept of human-robot teaming. And each of these senses play a very important role to get closer and closer between humans and machines.
And as you say, like, yeah, I don't think you think about it, but if you watch like a kid play around with thing, for instance, like, okay, give them an egg, they will certainly break it, right? And they don't know how to operate like such a fragile thing without breaking it. And same for the robots. Like if they just see an egg and they can't tell the difference between holding an egg and holding a stone, they will certainly break some eggs. And you don't want a robot which breaks all your eggs unpacking your groceries onto the fridge. So if they're going to handle these things, they need to learn. And toddlers learn through testing and experimenting. But yeah, the robots need to learn by experimenting and actually experiences this different thing and learn how to handle different things. And that goes even more into my master thesis, which I developed like glove, which will give haptic feedback and connect it to a robotic arm and hand. So we actually could make an operator operate like the robot though. So the robot didn't do it itself, but through teleoperation, we could actually have the robot team up with the human and grab the different things like eggs and more fragile things, and then also rigid things which need a firm grip, like a milk carton, which needs some force. So, and the operator can feel it and apply direct. So help the robot to understand, really.
And as you said, also you started mentioning the idea of learning, which is very crucial and is very much connected to the sense of touch. For example, when we start learning, even at school, right, we write down our note. We connect the concept with an experience that also involves forces, writing down notes and touching things. There are fields like, for example, medical fields, or where, for example, the surgical student needs to actually experience with his own hands what the doctor, the teacher is doing, because the only way to actually learn how to make a surgical operation is to use the bisturi and to touch the human body. So if we can use haptics and robotics to simulate this experience and to reproduce it in a bigger scale, then, for example, there is no need, or there will be less need for using cadavers to learn these procedures. And with this, I would like to connect to one project that we actually are closing. We are finalizing this month. That is Augmented Surgical Edu. It's a European project where we have collaborated with the University of Siena in Italy, with the KTU, Kaunas University of Technology in Lithuania, and with the Hospital of Life Science, also in Kaunas, Lithuania. So, Martin, this connection with learning also brings me to the next point that I would like to discuss with you, which is the ability that you have developed over time to design robotics platforms, robotics architecture, and some of them you have used them for learning or for teaching, and also the ability of building these frameworks, for example, using tools like the Robotic Operating System, or ROS, so that they can be designed in a modular way, and also they can be scaled to different applications. So, for example, you have also, I assume you're also using these designing methods for your ongoing project regarding battery disassembly. And tell us a little bit more about what you're doing right now and what are your plans.
Yeah. So the project that I'm working on now are really addressing the problems of like EV cars, because of course, as we know, EV cars has been one of the breakthrough in like carbon friendly transport, but the problem is with all these electric vehicles, they also need to be recycled, right? And if we don't recycle them, they won't be environmental friendly. We have to get more resources. And until now, it's actually been very difficult to recycle the EVs in a good way. So we're looking into how to actually optimize this process, all from like dismantling, which is more where I look into, and also further down into raw material refinement. But that's chemistry for now. But what we want to do is like, of course, if you're going to refine the raw material, it's better to have a clean product in. So if I give just a module with some few different components to the ones which is going to extract the raw material, they will probably get quite a good result. But if we just give them the whole pack with plastic, with cables, with a lot of different parts, they will have a much harder time. So we want to like pick out the components and sort it as much as possible before they go to further refinement. And today that process is actually done manually, which is crazy to think of, because there's so many EV batteries and there's a guy standing there and unscrewing the screws themselves for like every part. And in the long run, I don't think that can scale. Like you have so many people who, we need so many to actually disassembly them. So yeah, we're looking into how to automate it. And to do that, right, the main problem is like the batteries are fine when you're going to assemble them. You know how to assemble them. You know, there goes a screw there goes a part there goes zip ties there. But when you disassemble them, you can get any model in. So we need a way to like actually make the robot understand in a native way that how can I solve this puzzle? And that requires so many subsystems to work together. You need vision to actually know where are the components placed this time. You need decision plannings to know like, okay, first I need to do this and this and this. And then you need a planner to actually know where to move the robot. And then you need tools and tools programming to actually do the fine operations. And like designing these software programs which actually combine this but retain the individuality. So it can do all these things in a huge program, but it's actually many programs working together solving this complex problem.
So I assume that's where tools like ROS, the robotic operating system, can help building this framework of different nodes taking care of different aspects. And also from a more theoretical perspective, also, it's interesting to learn a bit more maybe about the concept of imitation learning. How are you planning to use that? And or if you have already started looking at this aspect, you can tell a little bit more about this.
Yeah, as I mentioned earlier, like the robots actually need to learn exactly how we learn. You can try to make the robot learn itself, so exploring all the possibilities. But in terms of robotics, there's so many possible configurations and movements. So exploring all of them would be like unrealistic, right? But just as toddlers, to draw that, uh, where they don't learn all by themselves. You give them an egg, and you probably just give them eggs, and they would keep throwing them, right? But you say like, "Hey, this is how you do it. You take one up, you carry it over, and put it down." So we can kind of do the same with robotics. We can make an operator control and like show how it to do it. You can either do it as like just controlling, steering the robot, or you could do like a teleoperation, as I told earlier, like actually remotely control it. All that matters is that you actually record the robotic operations while it do it. And then you can take that recording and tell the robot, hey, now, this is an example of how you should do it. But now you can test it on a little bit bigger egg or a brown egg or a smaller egg or a carton full of egg. Like you have to really make it apply these good examples on a larger range of examples to actually make it learn a broader range of skills, just as a toddler would. So it all goes back to we make the robots try to learn our abilities through how we learn them.
Nice, Martin. So if we would not want to break too many eggs, is there a way we can, for example, use a simulator where the robot can explore the simulated world and learn in that environment, and then we could bring this, export this experience into real world? Are you considering something like this? For example, Nvidia and other big players are already shown this opportunity, building very realistic physics-based simulators. Are you looking at this direction as well?
Of course, and learning, as we talked about, you need to break some eggs during the learning phase. Uh, so yeah, and if the robots, like we talk robots which are rated for safe 60 kilos, they are huge robotic arms. They can really break more than eggs if they go wild. And in the beginning, quite long actually, they will go wild. So yeah, definitely we need some simulated environments. And we're explored IsaacSim, for instance, which, as you said, is Nvidia's simulation platform, which is really good at simulating this physics environment. So we can actually like model up the robots and then model up the puzzle we wanted to train on, and based on the data, and we can let the robot loose and it can go for many episodes. So then it can train and train and train and train. The problem, of course, is this is heavy. This is super computational heavy. So not only are you going to simulate the full robotic and the full control system, but it also all the possibility and all the physics in the environment. So it's quite heavy actually to make them train for a long time on the computer and the load. So you have to be smart about it. You can't just let it loose. But yeah, you have to tell it and guide it. So these simulated environments are super important for us to be able to guide the process, but also explore possibilities, right? Because if it doesn't learn or it go crazy, no one's hurt. The environment can just reset time after time after time. It wouldn't be that happy if I did it in my lab and the robotic arm broke through floor, maybe, or it's expensive machinery. So we like to keep them quite tested in the simulated environment first, and then we can make sure it kind of behaves and should behave quite well, and then transfer them to the physical lab and test and over that it actually works. But that's also a problematic thing, right? Because this model we don't have fully control of them. So you can't just take any model and transfer it in, because you never know what it's going to do. It can do the same thing for like 900 or 9,000 times, right? But that one times it goes wild, it can have fatal consequences. So we need to also build in this safety constraints around it, both in the training and the simulation and the physical world. So yeah, so the robot and humans actually can team up together, and that we're not going back to this robots in a cage version because we don't longer have control for it.
Yeah, this is a very important point to define the constraints and to make sure that the system is completely safe and can replicate the same procedure in a safe way. And this is somehow, yes, it brings us to the progress from robots in a cage to liberated machines and so on. Because when we were using traditional control algorithms, one of the concepts we were always making sure was that the stability, for example, of the control algorithm. But when we use algorithms that are machine learning based, like imitation learning, then it's not possible to guarantee a complete transparent algorithm or a completely safe algorithm. But that's why we are trying now to merge these two worlds, the world of traditional control algorithms with the world of machine learning. And also, it came to my mind this idea of a puzzle box. You know, one of these boxes that you buy and you somehow you need to open because maybe there is a key inside or a present or a toy. And it's like something that for humans is very difficult already. Like you need to taste all the possibilities. You need to maybe go back and forth and remove a panel first, then the next, and then maybe it doesn't work. You have to start again. So it's like training a machine to open a puzzle box, but you're actually disassembling battery modules. So I think that that's very, very inspiring. And with this, speaking about inspiration, I would like to move to the next final point. If we close our eyes and we forget about the eggs and the broken eggs, and if we look ahead of us, short term, 5-10 years, but also medium term and long term, like 100 years from now, what do you see? Is this really happening? And what are the challenges and the potentials for this to happen?
It's definitely happening. It might not be tomorrow, and it might not be 5 years from now or 10 years from now, but it's happening. We need it, right? Back to like the battery disassembly, it's both like a scaling problem, but it's also a safety problem, right? Because it can be dangerous, a lot of these operations. So it's not just like for an economic benefit, but it will gain like a human benefit, not having to do these dangerous operations anymore. But you still need a human there for a long time, right? Learning human experience, we have usually a normal working person has like 40 years experience being a human. And although you might have an education and you're working in a job, you know this, you know how to use your sensors, right? You know how to use your eyes, your hands, your force. So, and all this is so important. And then a robot's going to suddenly learn it. It's unrealistic. We need to keep progressing this to a good way so we actually can apply it. So I think like tomorrow there will be mostly the same as we're now, but all this technology we'll see is incredible, right? There's so many impressive robots out there now doing operations which like 5 years ago wasn't possible at all, and now it's possible, but we still need to like generalize it. The toddler still needs to break more eggs and learn how to handle many different eggs. So I think it's really exciting, the looking forward in how the possibilities is, and for almost all sectors around us, like for construction, for machining, for industry, but also like human robots or human helps. And as we talked about, health sector can gain a lot from having these interactive robots helping us. And you say like surgery, for it can, for instance, in Norway we have a lot of problems with, we have a lot of remote places with small hospitals, which is problematic because you can't have the competence or the really good surgeon have to do a lot of surgery, right? He doesn't stay good forever. But if he's just at a small place, it's difficult for him because there's might not be that many operations, and it's not like an environment he can talk to others, learn more. So it's moved into the bigger hospitals so we can actually have a good quality. But how then can you do this surgeon at smaller places, right? And just looking into like, how can we then move this robot, right? So we can have the surgeon staying in a major city in Norway and then actually do the operations at a smaller place, but still having the environment around him and the training and the workload, which is he has to have to be a sufficient and good quality surgeon. And I think if we like think outside the box, there's so many places we can take advantage of this, which actually helps us. And it's not that frightening. It can seem frightening, I think, at first, like it's, oh, they're going to take over the world and run the world, but we're modeling them on ourselves, right, for helping us. So we're not building them to destroy us. And I think there's so many points like this where they actually can do a huge difference if we just like are able to think it. And some of these opportunities I think will come naturally. I think we cannot think of them today, but maybe in a year or something, a new use case is suddenly obvious. And so, yeah, I'm really excited to see if it's working or when it's going to work. I think it's a question, not if.
Yes, it's nice to look at the future, and as our song, our anthem, the lyric says, we are stronger when we are teaming. So it's not about replacing humans, but it's about working together. And I was also thinking about leaving our listeners, especially young listeners, with a comment about your progress from student to PhD fellow. And would you like to tell them something? What should they focus on? What, how should they approach their studies and think about their career? Yeah, it's inspiring to see your progress, Martin, and I guess it's nice for the young listeners to connect.
That's a big question, though, maybe, but yeah, and I think of course, I did my bachelor, my master's, and now my PhD on my PhD. But for me, it all goes down to I do what I love, right? I often say like I would do this anyway. I wouldn't be able to not touch a robot or do some programming or automate a task or exploring the possibilities with this technology. It just I think it's so fantastic and it's so enticing me that much. Like I need to do it, kind of. So when I started at mechatronics, I thought I had some vague idea of what it is. I did try to build some robotic stuff earlier when I was smaller, but really few resources, and I didn't have ChatGPT back then, so I really had to learn all of it myself from the bottom up, which maybe was smart because I learned to learn this thing quite early, right? Although my project really didn't work out, I tried to build a drone myself, but it was more a killing machine in the end because it was so super dangerous. But I learned so much from the project, and when I started here, I just kept on going. Like I saw every opportunity, every subject as opportunities to learn something new. Most of the subjects, at least. So yeah, and keep taking the opportunities, right? When you're enjoying what you do, you tend to do a little bit more, explore a little bit more, and people notice that. So then you get opportunities to do other exciting projects, as the research project I've done together with you and others also really allowed me to explore this research approach to mechatronics, and not just building something, but actually developing new technologies. And I just fell in love with developing new technologies. So here I am trying to do my PhD. It's more challenging than ever. It's probably supposed to be, but I keep loving it. So we'll see how far it takes me. But yeah, so the only advice, you said like some advice for young listeners, I think it's just like, if you find your thing, then allow it to entice you, like allow it to have fun with it and explore it as much as possible. And I think a lot of work may seem pointless at the beginning, and then it goes a year or two and you really see how important it was and what it gained you, even though it didn't seem it back then. So it sounds stupid because it's what everyone says, right? But give it all and just give it your all, and I think it will be fine.
Nice, nice, Martin. So a short summary like that I like to point out, like learning to learn. So it's really the skill that can make the difference. And also, of course, at the base, you should have your own self-motivation, and then the doors will be open. So I remember a couple of projects we did together, from prosthetics and soft rigid actuators. And then I have some good memories. We were in Malta for the IEEE Robotics Championship. That was also an experience, and also like being part of a team. I think it's something that keeps us motivated, and the thing that we can help with each other is something that even in a small team, like we are in probably one of the smallest university in Norway, we can reach out to people and we can share our experience. And that's one of the goal of this podcast. We want to reach out, we want to promote the activities we are doing, and we are also very open to get critiques and to get and to learn from the others. So with this, I would like to just conclude this podcast, and I leave you, Martin. Would you like to say a few concluding words?
I don't know. Thank you for having me here. I really enjoyed talking about my research and my work, of course. So this was really nice. And as you say, like, I think mechatronics is so important for the future. And really, we have so much work going on here. Not good work at our university, which is not one of the biggest one, but still, I would say an important one. So just an exciting future ahead for all of us.
Great. So with this, I leave our listeners with our traditional finishing song. Enjoy it, and remember that they are among us, human-robot teaming. See you next time.
Among us, not alone in innovation, shared control, shared creation, rewriting Augmented. Human robot teaming. Human robot through the noise of doubt and distance, through the fear of what may be, we found trust in every motion, in shared autonomy. Not replacement, not surrender, but a fusion of design. Intelligence extended, your decision joined with mine. Oh, we rise together in the space where futures start. Oh, not rivals, partners, code and courage, mind and heart. Among us, stronger when we're teaming, human hearts and circuits dreaming. Side by side we stand. Among us, shared control, shared believing, human robot teaming, shaping what we are. Is it steel? Is it soul? Is it logic taking hold? Is it fear we leave behind when two forms of thought combine? Hear the signal, feel the spark, we ignite the among us. Now the future's breathing, human minds and systems